The first video from chapter 31 I'm going to talk about Gauss's law for magnetism, and this is covered in chapter 31-1 of the textbook. Alright, so first off we need to define magnetic flux. So think back a couple chapters to when we did electricity, and in particular Gauss's law, and remember electric flux. So this was Gauss's law. So the electric flux, which we calculated through, if we were calculating through a closed surface, that's what the circle means, and it's E dot dA, and we do the integral over that. So similarly, we can define the magnetic flux. And for the magnetic flux, well, basically instead of using electric field, we use the magnetic field. So to calculate magnetic flux, it's going to be the integral of B dot dA, and then we integrate over that area. So the units, well, they're Tesla times meter squared, field times area, and the SI unit, Tesla meter squared, is also known as a Weber, and that's a WB. Alright, so now that we've got magnetic flux, we can define Gauss's law for magnetism similar to what we had for electricity. So remember, for electricity, Gauss's law said that the electric flux through a closed surface is proportional to the source charge enclosed, right? Qn over epsilon naught. However, remember that for magnetic fields, we found that there's really no such thing as a source charge, right? So they're due to currents, and there's no such thing as magnetic monopoles. Well, if there is no magnetic source charge, well, then the source charge is zero. And so the magnetic flux through a closed surface must always be zero. So that actually gives you Gauss's law for magnetic fields. So the magnetic flux through a closed surface now has to equal zero. So that's Gauss's law for magnetism. Of course, since it's always equal to zero, it means that it isn't terribly useful for actually going and calculating much of anything.